In this problem, a given aerobic digester has a 50-foot diameter and a height of 8 feet. It is capable of treating 8,000 gallons per day of thickened secondary sludge and has a volatile solids loading rate of about 0.04 pounds per cubic feet day. If 60% of the matter in the digester is volatile, what is the solids concentration of the sludge in the digester expressed as a percent? So the first thing we need to do is use our reference manual. The problem is asking us to find the solids concentration. If we search solids concentration, this will bring us to Chapter 6, Section 6.8.5.3, to a section below activated sludge treatment called Solids Loading System. And this will be on page 455. So looking at that equation, we can write it down as follows. So SL equals 8.34 QX, where SL is the solids loading rate in pounds per day, Q is the volumetric flow rate in million gallons per day, and X is the suspended solids concentration in milligrams per liter. So let's start looking into our problem to see what things we can fill in. We have flow, but it needs to be converted into the proper units first. So Q equals 8,000 gallons per day, converted so that 1 mgal over 10 to the 6 gal, and this is going to give us 0.008 mgal per day. We've also been given the volatile solids loading rate in units of pounds per cubic feet day. Note that the reference manual wants this in pounds per day. So if we write this out, we can see what terms are still missing and guess how to solve for them. The reference manual also contains the units for the 8.34 conversion number here. And that's going to be pounds over mgal all over milligrams per liter. Now Q we just solved for, and that's going to be 0.008 mgal per day. And then finally X is going to be milligrams per liter. And also we can include the 60% number here now as a decimal to account only for those matter that are volatile. So if we start crossing out units, we can see what's missing. So the only thing left to solve for is going to be cubic feet. How can we do that? Well, we've been given the dimensions of the digester. So if we want to get the solids loading rate here into pounds per day, as is requested by the problem or by the reference manual, we can simply use the volume of the tank to find the loading rate in only pounds per day. So let's do that. So note that we need to realize that the digester is going to be a cylinder. So we can calculate the volume of the tank and then find the loading rate in pounds per day. So the equation of a cylinder is going to be pi d squared over 4 times h, which for us is going to be pi 50 feet squared over 4 times 5 feet. And the volume here is going to be 9812 cubic feet. Updating the equation here, therefore, we can see 0.04 pound per cubic foot day times 9812 cubic feet is going to give us 392.48 pounds per day. So if we update our equation one more time, we can get 392.48 pounds per day equals 8.34 pounds over mgal over milligrams per liter times 0.008 mgal per day times x in milligrams per liter times 0.6. So once complete, all of our terms are ready to be crossed out so we can solve for x. So x here is going to be about 9804.16 milligrams per liter. Finally, we need to know how to convert x given in milligrams per liter into a percent, as that is what the problem is asking for. So we can use a rule of thumb. We can use the rule of thumb to see that every 1% of solids concentration is equivalent to about 10,000 milligrams per liter. I'll expand on this in a second. For now, we can set it up like this. And since we have close to 10,000 milligrams per liter, we can see that our answer is about 1%. So I'm sure you are wondering, why? Where does this come from? So what's the supporting math behind this rule of thumb? Let's go through it. So we can start by saying 1% solids concentration is the equivalent of 1 kilogram of solids per every 100 kilograms of water. A unit conversion here, we could say it is equivalent to, there are 1 million milligrams of solids in 1 kilogram of solids. Next, we would have to know that 1 kilogram of water is the weight of 1 liter of water. Simplifying this out, we can get 1 million milligrams over 100 liters, otherwise known as 10,000 milligrams per liter. So that is where this rule of thumb comes from, and you can find it in other references to wastewater engineering. So to solve this problem, let's review. You need to know the following things. The first thing is going to be you need to know the correct equation to use, which comes from the reference manual. Next, you need to recognize that you're only concerned with the volatile matter. So even though the equation itself doesn't give a spot for the percentage of volatile matter, this 60% will still play a role. 3, you need to know that the tank is a cylinder when you're solving for the volume, so that you can get your loading rate into the correct units. And 4, possibly the most important part here, is you simply have to know what this rule of thumb is to make your conversion from percents to milligrams per liter, or reverse, depending on what the problem might ask of you. So there's a number of steps here, and some of them do kind of require background knowledge of some aspects of wastewater engineering. However, if you can keep things like this in mind, this rule of thumb, because I don't think it's in the reference manual. The remaining steps in the problem you should be able to figure out. I guess also knowing to apply the 60% number here. So yeah, this is probably one of the more difficult problems I think you would see on the exam. But if you can keep these steps broken down one at a time, you'll be able to solve it.